right. Good morning, everybody. Hope you're all feeling better than I am today. And there are a number of people absent um, earlier this week, so I hope everyone is back and feeling pretty good. Um, this morning, we're going to talk about friction, and we're going to hit a few different things. One is that we're going to kind of recap the differences between static and kinetic friction. And then we're going to think about our model of friction and the specific attributes, properties of materials and surfaces and objects that are involved um, in determining how much friction will exist. And then what I really want to kind of hit is two big things. One is the difference between how static friction and kinetic friction um, affect the motion of an object, the magnitudes of those forces, and how they affect the motion of an object. And then the other is the role of the surface types in determining the amount of friction on an object. We're going to look at three main types of friction. We've already looked at static friction. This is the friction that exists when an object would move if there were no friction. And this is largely what we were looking at with the friction investigation and with the model of friction activity. You can think about static friction um, as being the force that prevents something from moving when, in the absence of some other force, it would start to accelerate. So it's kind of hard to imagine, well, how do we know if an object would accelerate if there were no friction when there is friction? And um, the best way to do it, I find, is to just sort of imagine that we're turning off friction in our brains. And a lot of times, that's all it takes. So if you think about the classic object on a ramp scenario, for example, if you have an object sitting on a ramp and there's no other forces acting on it, it's just sitting there. Well, if there were no friction, it would start to slide down. If you put it on wheels, it would start to slide down. If the surfaces were really slick, it would start to slide down. Or if you're pushing on an object, if you're pushing on a box and it isn't moving, even if it's on a level surface, if it were on wheels, it would start to move. If it were on a really slick surface, it would start to move. And so if it doesn't, there must be some other force that is acting in the opposite direction of the applied force. That's got to be static friction. Kinetic friction is what you get once an object starts to move. And this is easier to kind of see in action because if you know which way an object is moving, then you know that there's kinetic friction acting in the opposite direction as long as it's sliding on a surface. And we are going to think about rolling friction pretty much the same way that we think about kinetic friction. It isn't, but effectively we can model it the same way. And there's only a couple of weird circumstances where it wouldn't work, and we're going to conveniently ignore those circumstances. For all three of these types of friction that we're going to investigate, the nature of the surfaces matter. We figured that out when we did the friction investigation. Um, and then when we did the model of friction activity, you all saw that there was a linear relationship between the normal force and the force of friction acting on an object. And it turns out that we have a variable that we use um, to in place of the word coefficient, and that variable is this weird one right here. It's mu. It's the Greek letter mu. It looks like a U with a little tail in front of it, and it's m. It's spelled mu, and this is the coefficient of friction. This essentially tells us how frictiony two surfaces are, and it can be very, very small. For surfaces that have very little friction between them, it might be close to zero. Our supercarts have a mu of very, very close to zero when they're moving. It's virtually no friction at all acting on them. Mu can also be really large. Theoretically, it could be almost infinite. In practice, it tends to be less than one. And that's not um, because of any um, universal laws of physics. It just happens to work out that most surfaces are a little bit easier to slide relative to one another than it would be to, say, for example, lift an object up. So that means mu tends to be less than 1, but it's not always less than 1. And don't fall into a trap of thinking that it has to be less than 1. Mu can be very, very, very large. Surfaces that are incredibly frictiony have a very large mu. Think about a piece of tape. If you were to try to pull a piece of tape that was stuck to a surface horizontally, effectively that's friction that's preventing you from pulling it horizontally. That is a lot of friction. It's way greater than the normal force that's pressing those two objects together, the tape and the table. All right, let's take a look at static friction first. So static friction is kind of complicated because it can change not only in direction but in magnitude. Static friction prevents an object from sliding. So we only have static friction when an object is motionless and stays motionless. You can't have static friction if an object is moving. So what that means is that the direction of static friction depends on the overall applied force acting on an object. If you push an object one way and it doesn't move, then static friction is pushing the other way. If you pull an object a different way and it doesn't move, then static friction is opposing the motion of that object the other way. An object that's motionless on a ramp, in the absence of any other forces, is going to experience a force of static friction up the ramp. It's preventing the object from sliding down. But we can create forces of static friction in any direction by creating overall applied forces in any direction. If I have an object on a ramp and I push on it up the ramp, if I apply a force up the ramp, then I can potentially eliminate or reverse the force of static friction. If I'm pushing hard enough on an object that if it was on wheels, it would slide up the ramp, then the force of static friction is opposing that upward acceleration. Force of static friction is down the ramp. So static friction is not necessarily predictable just by knowing an object's orientation in space. It's all the other applied forces that determine this, the force of static friction. And the magnitude of static friction is variable as well. And we saw this with the force of with the friction investigation and the model of friction activity. We saw that we could change our overall applied force on an object. If we tilt a ramp, the parallel component of the gravitational force was increasing. The object was not sliding yet, though. So the force of friction opposing the motion of that object must have been increasing. We saw that with the model of friction activity as well. As you increased the applied force on the force sensor, as long as the object wasn't moving, the force of static friction must have been increasing to be equal and opposite. If you apply a force on an object and it doesn't accelerate and there's no other forces, then the force of friction must be equal and opposite. If you increase that applied force, the force of friction must increase as well, as long as that object doesn't start to move. If you eliminate that applied force, then you got to eliminate the friction force as well. Otherwise, the object weirdly would move in the direction that it's not being pushed, which doesn't make any sense. So a lot of objects are experiencing very little static friction. So that means that we can calculate the force of static friction by knowing something about the surfaces, right? This is the surface type, and something about the force between the surfaces. That's the normal force. The force of static friction is going to relate to the the surface type. That's our mu, our coefficient of friction that tells us the stickiness of the two surfaces involved, and the force that's pressing those two surfaces together, the normal force. The tricky thing about static friction is the magnitude is always going to be less than or equal to that. We don't know how much it is unless we know the net applied force from all other forces parallel to a surface. Much of the time, what we're really trying to determine with static friction is what's the maximum it could be. The maximum that force that static friction could apply is this coefficient times the normal force. Okay, so that's what that means is If the overall applied force is greater than that, it will start to accelerate. Okay, that's so sometimes we're looking for a frictional force that's less than that maximum. If we have an object that's experiencing a small overall applied force, but not accelerating, not moving, then the force of friction is going to be less than that maximum. Sometimes what we want to know is what's the maximum overall applied force we could apply to this object without it starting to slide. Right? So that's static friction, and that's largely what we've been working with up until now. Kinetic friction is like static friction. It opposes motion. With kinetic friction, we have an object that's sliding along a surface. So kinetic friction, it's much easier to determine the direction. You just watch it. If it's moving, it is experiencing a force of kinetic friction in the opposite direction of its motion. What's weird about kinetic friction to us is that the magnitude of the frictional force is constant. It doesn't change. It doesn't change depending on other applied forces. It doesn't change depending on an object's acceleration. It doesn't depend on an object's velocity. It's always the same. So if we have a motionless object and we push with a greater and greater and greater force and it does not accelerate, doesn't move, then the force of static friction increases the whole time that we're increasing our pushing force. But once it starts to move, the force of friction no longer changes with our applied force. We can push with more and more and more and more and more force. Our applied overall force could be really, really, really large. The force of friction stays the same. It could be accelerating, the force of friction stays the same. Even if the applied force drops to zero, the force of friction stays the same. So static friction is variable in magnitude. Kinetic friction is not. Kinetic friction is always going to be less than static friction. We know that, and we can kind of reason it out by imagining that if we're pushing on an object with an ever increasing applied force, and our force of static friction is increasing and increasing and increasing, and then we push a little bit more and it starts moving, but the force of kinetic friction is greater than the force of static friction, then there's a larger force opposing or pushing force, which means it couldn't have started moving. And so that's a paradox. That doesn't work. In order for an object to start moving, it must experience a drop in the frictional force. We can't continue to increase the force of static friction or the force of friction with an applied force and have the object start to move. It won't work. So that means the force of kinetic friction has to drop as an object starts moving, and then it stays constant. So we get this characteristic graph of static versus kinetic friction. This lower screenshot here, I did not take this data, but this is showing an overall applied force that was used to calculate a friction force, the same way that we did in the model of friction in the friction investigation. And you can see that as this object is not moving, the applied force increases, indicating that the force of static friction increases until it reaches some maximum. And then once the object starts to slide, boom, the force of friction is constant. We could use this maximum force of static friction to calculate the coefficient of static friction if we knew the normal force. And we could use this constant force of kinetic friction to calculate the coefficient of kinetic friction if we knew what the normal force was. Kinetic friction, like all forms of friction, is only related to the nature of the surfaces involved and the normal force. And it's a little bit easier to think about in terms of an equation because it's constant. So we don't have a less than or equal to in there. The force of kinetic friction is simply equal to the coefficient of kinetic friction times whatever the normal force is. Okay. Rolling friction, we're just going to look at briefly. I'm not going to go into details about this. Essentially, what we can think of with rolling friction, it's really more accurately looked at as rolling resistance. It's not quite the same as a frictional force, but it ends up working the same. It ends up opposing the motion of a rolling object. It's constant. The causes of rolling friction are a little bit different than the causes of friction. Rolling friction is caused by deformation. So if you have a round surface, say on a flat surface, the flat surface kind of dents a little bit, and there's a little bit of a bulge opposite the direction of motion, and so you get this weird like pushback from surfaces. It's not visible typically. I mean, you could see it if you had, a a sturdy bearing or cylinder on a real soft surface like rubber or something like that, or clay. But most surfaces we don't see this, but it's happening on a microscopic level. The other deformation that occurs is that the rolling surface, the round surface, actually flattens a little bit. And then there's some stickiness. It's the surfaces stick together a little bit, and the end result is this really complicated pattern of normal forces that's determined by the nature of the materials, including wheels and bearings and axles and everything else. And it's really kind of crazy. And essentially, it all boils down to something that looks almost exactly like kinetic friction. It's constant. It opposes the direction of motion. If we know the coefficient, we can calculate the force of friction. We need to know the normal force as well. And so what that means is that we're going to use it essentially the same way that we use the force of kinetic friction. We need to know a little bit about rolling friction in general, because it affects some other stuff. But we're not going to be using that in this class. Physicists need to know this, but we are going to be spared from needing to work through these crazy calculations, because we are going to conveniently ignore the paradoxical situations that could result from kinetic friction involving rolling surfaces. When we work with friction, I've mentioned a whole bunch that the force of friction is related to some coefficient times the normal force. And so that means if you know the coefficient of friction and you know the normal force between two surfaces, perpendicular force acting from one surface on another surface, then you can find the force of friction that's acting on an object. But we often don't know those things. You look around the room right now and think about the objects that are in this room right now. We don't know mu at all. And we might be able to find the normal force by making some measurements, but we don't know that offhand right now either. So very often what we're going to be doing with friction is dealing with it as if it's just another force, like an applied force, a force from tension, a pushing force from a person, a object pushing on another object. We're just going to imagine that force of friction is just a force. In the absence of knowing anything about mu and the normal force, we can calculate it the same way that we calculated it in the friction investigation in the model of friction activity, which is to use Newton's second law. Okay, where this equation comes in, this friction equation with mu and the normal force comes in, is that it's an additional equation for finding additional unknowns. We might be given mu and the normal force, in which case we could find the force of friction. Or we might know or calculate the friction force. We might be given this force here, and you use that to either determine the normal force or mu. So it expands our universe of things that we can find. In general, if we're going to be dealing with friction in a problem involving forces, what we are going to do is we're just going to think of it as a force. We're not going to think about the mu part of it. We're not going to think about the normal force part of it. We're going to start by just thinking about it as a force, which means we need to know what direction it's in, which can be confusing. If it's moving, we know the force of friction is opposite to the direction of motion. But if it's static, we can't assume that we know the direction of the force of friction. It may be that there's an obvious scenario, like a motionless box on a ramp with no other applied forces, in which case we can correctly assume that the force of static friction, like it is in this diagram, is pointing up the ramp. But if there's some other force acting on this box, if there's a person pushing on it, and we don't know much about the magnitude and or direction of that pushing force, we may not know the direction of static friction. A person, as I mentioned before, pushing up, if there's an applied force on this box up the ramp, that could reduce, eliminate, or reverse the force of static friction. We could also have forces that are not aligned with the parallel component of the force of gravity. We could have forces parallel to this surface that are straight across. We could have a force that would be straight into the box as we're looking at it, or straight toward us as we're looking at it. All of those forces would change the direction of the force of static friction. In general, I'll try to be real clear with you. When I give you a problem on a test or a quiz, can't guarantee that problems in the book or in the internet universe are going to be as clear as we need in order to determine the direction of static friction. Sometimes we will just not know. Other times we'll have to make some sort of an assumption. Sometimes we'll have to just say, okay, well, let's assume it's not moving, and then we'll progress from there. We might be wrong, but we have to make that assumption. Okay. Once we've identified the direction of friction, then we want to think about whether the friction is static or kinetic, because that's going to affect the magnitude of the force. If it's static friction, the magnitude is variable. If it's kinetic or rolling friction, then it's going to be a constant. And then we'll draw a free body diagram that shows the force of friction on it, and we could potentially use that free body diagram along with Newton's second law in one or more dimensions to find the force of friction, even if we don't know mu and the normal force. That's what we did in the investigating friction activity. That's what we did for the model of friction. And that's what we're going to do either later this week or on Monday when we start looking at carts that are accelerating and we start thinking about the force of friction that's acting on those carts. And we'll work more with this as we start getting into problems where we have more information about friction and the normal force and stuff. We'll start looking at this more. You're going to play around with this a little bit today in today's activity, and hopefully you kind of get the feel. The big problem is that if we have a force in Newton's second law, that's the force of friction, we could potentially use it in this equation. If we know enough about normal forces and coefficients, we could potentially use it in this equation. There's more than one equation that the force of friction shows up in. So if you're asked, what is the force of friction acting on an object, you shouldn't assume that you're going to use this equation. You shouldn't assume you're going to use this one either. You have to figure out what you know and then use what you know to find the force of friction. It might be a bunch of other forces and acceleration, in which case you're going to use Newton's second law. It might be normal forces and coefficients, in which case you're going to use one of our friction equations. All right, so to kind of put this all together, what we've got with friction is a model in which we are essentially going to be using two equations that relate surface area and the normal force. One that is a variable force of friction, both in magnitude and direction, that's equal to the coefficient of static friction times the normal force. One that's constant in magnitude but variable in direction, and that's going to be equal to the coefficient of kinetic friction times the normal force. The surface area of the objects in contact doesn't matter. The material that makes up those surfaces does matter. The type of surface is really critical. Some things are more frictiony. That is what determines the coefficient. And remember, that could be greater than 1. Things can be really, 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 really sticky. And then the normal force matters as well. And remember that while often the normal force is going to be equal to or proportional to the weight of an object, it's not always. Okay, what we really know is that the sum of the forces perpendicular to a surface are going to be equal to an object's mass times its acceleration perpendicular to that surface. The normal force is at least one of those forces. There may be others as well. So if there are other forces, or if there's perpendicular acceleration, then the normal force is going to be related to the weight of an object in a pretty complicated way. If there aren't other forces and there's no acceleration perpendicular to the ramp, then in general, the normal force is going to be equal to the weight of an object times the cosine of the angle of the surface relative to the ground. But that's only true if there's no other perpendicular forces and no perpendicular acceleration. Okay, so this is not a universal equation that we can use. It only applies in the absence of any other perpendicular forces besides the perpendicular component of gravity and the normal force, and it only happens when there's no overall perpendicular acceleration. Okay, so at this point, you all have enough information to get started with today's activity, which is going to be to use a simulation to explore really the shape of this graph, which shows how we can increase an applied force up to the maximum force of static friction without causing an object to start moving if it's motionless. And then once we've done that, then we're going to get a constant force of kinetic friction opposing the motion of an object. So you'll have a bunch of time to explore the relationship between applied forces, static friction, and motion and kinetic friction.